This video is about the journey of correcting this to this. My expectations of this motor led me to believe this would be a 1 or 2 week flip with minor costs. So I started to address the parts as I took them off. Pulling the heads off the motor caused me to step back. But at this point I still thought I had a quality build at the lower end. Astonished at the block deck surfaces, I had to choose what to do here. I invested poorly with this motor, and I'd rather not go deeper into the hole. So at this point, I'm still thinking head gaskets, one lifter, and a rear seal. The bores looked good, so I don't want to disturb those. I did a piston protrusion check, and the front cylinders did leave a considerable margin for machining. A good machinist might be able to shave this slightly. However, my normal approach is decking is done off the crankshaft bore as the reference, so that would mean pulling this motor down all the way, and a lot more money going into this already expensive investment. I'll do it if I have to, but I need to try something creative. And I have a method of cleaning the surfaces that has worked well for me over the decades. I realize there are people out there who deck the motors using the previous surface as the guide. It's a workable method, but it can further move the deck plane away from where it should be, affecting compression and lifter engagement. The proper way is to use the crankshaft bore, and the camshaft bore as a guide to establish the deck angles. It's also the way the cylinder bores should be machined, square and 90 degrees with a solid boring bar. Initially, International and Ford wrote in their service manuals to use non-metallic brushes and scrapers to clear the surfaces. But I think with dealership service personnel using razor blades, steel bars, and rotary abrasives, discussing that online, a new TSB was released by Ford, basically reinforcing the narrative in the manuals. Not to use steel scrapers or razor blades, which can scratch or gouge, providing pathways for combustion gas to flow and bypass the sealer. Someone should explain the issue to Ford's rebuilder. They also don't want anyone to use rotary abrasives or abrasives in general. I never use a rotary abrasive tool on the decks or heads. I will use them on other surfaces that are not as critical for flatness. To me, this is just not a problem-solving technique. Ford now insists you use a brass scraper, so we've changed from using non-metallic to non-magnetic. I have a brass scraper, but typically don't use it for this. I will use it in this case, as I don't want to give someone a reason to question my findings. The Scotch-Brite 96 pads I've always used in cleaning. It's a good scrubbing tool. Ford is okay with surface staining, but I'm not. My viewpoint is any debris left behind can affect the adhesion of the gasket sealant. It's why I do this. They state impressions from the previous gaskets are acceptable, and I've never worried about those. I'm also okay with corrosion and erosion of the coolant areas not impacted by gasket sealing. I'll use a segment from a cylinder head video I'm working on to show my standard procedure. I place paper towels on the surfaces I'm going to clean, then soak them with the spray gasket remover. This prevents the spray from going into areas that are difficult to clean. I then cover the paper towels with plastic so the chemicals won't evaporate quickly. And I can let this soak for hours. Sometimes I respray the towels during this period. I typically use Goodson Super Scrapers. They're expensive. They have a carbide block on the end to maintain their edge, and they clear the surface by plowing the debris off. If you look at some of Felpro's videos, they're in the background. Properly used at a low angle, I've never developed scratches. But they cannot clear out the material that's within the machining marks or shallows. And that's where the Scotch-Brite comes in. So while the surfaces are damped with gasket remover, I use the Scotch-Brite 96 pads as a scrubbing tool, just as Ford had recommended. Then clean up with paper towels. For this video, my starting example is the passenger side deck of the Ford remanufactured motor. Reaffirming, I use the brass scraper and Scotch-Brite pads. It's been media blasted by the rebuilder for whatever reason, but you can still see the fly cutter marks in the shadows. What I don't know is if this is an OE machine surface or an aftermarket machine surface under all this. But at this point, the surface has been cleaned per Ford instructions, and it still has the staining they allow. There's no direction from Ford or International about the surface finish specification of decks or heads, except replace if out of flatness. Industrial machinists follow specifications for flatness and surface finish. They're trained to read this. So for me, I don't understand the reasoning for lack of specification, except the obvious, no machining allowed at all. I've never been in an industrial machine shop that doesn't have a profilometer. It's the equivalent of a ruler to a carpenter. And yet there are automotive machine shops that don't have them, and engine builders that don't. If you own $100,000 in your equipment, how about $2,500 for a measuring tool? Or at least demand a printout of the surface finish from the machinist. How do you know if the work was good? Larry Carley is one of the most proficient writers to the service industry. In one of his articles for Engine Builder Trade magazine, he discusses surface finishes. The bottom line is under 30 RA for a stock MLS gasket, and some companies provide a thicker sealant for rougher finishes up to 60 RA. He also mentions RZ gives a better indication of the texture of the surface, and I've always used RZ. If you ask Data Tech Service, they say under 40 RA. And from Felpro's literature, they state OE is within the range of 20 to 30 RA. And their line of gaskets use a thicker sealant, which can go to 60 RA. And for many people, these finish measurement terms are a foreign language. So what's 30 microinch? Pretty damn small. To accurately measure a surface finish, you need a profilometer. And if your machine shop doesn't, just walk away. Otherwise, you're paying for guesswork. The profilometer measures the surface and can display the finish in many parameters. As mentioned, RA is common, but it's a narrow reading of the entire surface. RZ is a better measurement as it averages over 5 sample areas, and can better indicate the variation of the surface. I often use RT as well, so I'll know how deep the roughest marks are. It becomes my lowest point baseline. In this example, we can see why RA can be problematic. Completely different surfaces for the same RA. So with this, I have a spec for Felpro gasket, and I believe what is the OE finish requirement. And depending on what grit size was used for the media blasting, maybe this won't be so bad. Again, how well the machining under the media blast is another factor. After another Scotch-Brite 600 grit dressing of the surface, I would ask how many would say this surface is good to go for head gaskets. And that would be wrong. So putting all these measurements into a table, there is not one that meets the OE requirement for surface finish, RA or RZ, and only 3 of the 8 locations would be within the more generous ability of the Felpro gasket. I hope the international factory-built motors are not like this. So with a surface that looks like this, even if using head studs, we have the potential of head gasket failure in the future. Maybe 10,000 miles, maybe 50,000 miles. It's all a guess. Just like visually guessing what the surface finish is. Which brings us to, what's an ideal surface finish? Let's go back to Larry Carley's article. He says for an MLS gasket a surface finish of 20 to 30 RA is smooth enough. But he also stated that if you could get into the low teens or single digits, it would be great. So I posted the question to Felpro. Sentence after sentence is to go as smooth as possible. The smoother the surface finish, the easier and the better it is for the gasket to seal. And if we look at Felpro's MLS gasket surface finish, all these layers mate together. This chart shows that many cutting operations like milling take some above standard work to generate a finish below 32 RA. It's doable, but it takes some care. With abrasive finishing like grinding, honing, or lapping, it's much easier to achieve the smoother surface. And we all rely on abrasive machining for our motors. The stoning of decks and heads is kind of a backroom discussion. People say they do it with some reluctance, but there's not much information forthcoming. And some of that reluctance is probably due to they have no measurement of how well the abrasion really does. Using a body tool is abrasion, but the flexibility is not a good control for flatness. And this sure isn't. You can't control the consistency. You can just see the waviness left behind. Machinists use stones all the time, but differently. To clean burrs off the mounting surfaces, or lightly dress the edges of parts being made. And there's not one of my stones I would use as a prep for a deck or a head. And then the question, how flat is the stone? If we have undulations or disparities of the surface, and we use something that's not flat, we have single point contact, and that will not improve flatness on the surface. Nor will a 2-point contact, and you can cause other issues more problematic. A flexible or concave tool will cause a higher removal rate right where the gasket needs to seal the most. And so will an object that is convex. With a too short length, it becomes difficult to keep the object flat and not bite with the leading edge, or the trailing edge. So you need something that can be kept in good contact and bridge the gaps of the cylinders or other openings. The immediate reaction to this is that's what a mill is for, and while it improves the situation, there is always a force reaction of the tool bit when it's removed and engaged, which is how you end up with the deepest gouges here. I also use stones in my woodworking hobby to maintain chisels and planes, but as they wear unevenly, I flatten the stones with a lapping plate. The one I have has a large area, which helps in developing a flat surface, and it's certified to win 1/2,000th of an inch in all directions. It has a 160 grit diamond surface, but that's pretty coarse. It works well for truing stones, and a diamond surface would tear up iron, even though the grit is within an acceptable range. but it's suitable for holding things in place. My technique is the same technique as stoning, and was shown to me almost 40 years ago by machinists in our corporate experimental machine shop, by two guys who also raced in Englishtown. I needed to correct the surfaces of a small block Ford when a machine shop I was using didn't produce a finish that I cared for. And from some people's perspective, I can certainly understand skepticism about doing this. In 30 years of R&D work, I've done a lot of out-of-box thinking and projects. I'm not telling anyone else to try this. It's a skill set. But it's worked for me over 40 years to clean and correct surfaces, including decks and heads. Many might say you can't achieve precision work by hand, so I'll detour into that. These guys are spending thousands of dollars learning a technique I was exposed to decades ago. Hand scraping brings precision equipment back to specification. Surface grinders, milling machines, and lathes. It's an interesting craft. And in the case of this video, turns a straight edge into a precision tool. First this was milled, then it was surface ground. Finally it's hand scraped into a precision gauge for flatness. Not that I'm proposing scraping of a deck or a head, but this shows precision work can be done by hand. This individual and company have great videos of industrial machining, and along with the scraping technique, a good one on the lapping technique I learned decades ago. But you can't use a normal lapping motion with a cylinder head or block deck, unless you have a big granite surface plate. So I flipped the process on its head. The pattern here has to be a cross pattern that gives the best opportunity to flatten a plane. And I'll show the process first before the achievement. I'm calling the technique lapping, using the definition as smoothing and flattening the surfaces with an abrasive to a controlled finish. This is a latter stage, when I'm doing this right before installing the heads, the final finishing. At this point, I'm using 220 grit paper. It's a slow process, and I painstakingly try to make sure all the surface areas have the same amount of abrasion, and that's critical. I don't use any force against the surface, but let the weight of the assembly do the cutting, so there's no distortion of the plate. This is a long segment, but I think it's important to show all of it. The handle is one of my welding triangles. My holders, small super magnets. This direction of the plate in this manner is for flattening the width. And I'll fast forward sections so you're not totally bored to tears. And in this manner for lead flattening. During this process, as the deck becomes smoother, you can see the reflection improving. The guys at the experimental machine shop handed me a Blanchard ground flat steel plate. They set it up to hold sandpaper and installed a handle, and later on they made me one. I'm showing this with something anyone can buy, but if you get a steel plate ground, you could use that too. After trying this lapping plate, it holds the sandpaper better, and I think my old plate won't see much work in the future. And my hand position changes when necessary, to do my best to keep the plate flat to the deck. The experimental machine shop wasn't a typical machine shop. As part of the research center, they had the best equipment and great personnel. Along with the experimental foundry next to it, they manufactured the hatches for ballistic missile submarines. It's not an item that tolerates poor work. Now that I've shown the technique, let's see how it works. So after the first round of lapping, I'm clearing the high point. There are only 2 locations that meet the OE finish requirement, but overall this shows an improvement. All but 2 locations would work with the Felpro gasket's more generous allowance, so I'm getting there. So how did these decks change visually? Cleaned, no lapping, and after the first lapping with 150 grit. Most of the change is here at these 2 locations. With the older style composite head gaskets on the 289 hypos, the step 1 measurement showed an acceptable surface finish. Normally I've gone to the step 2 process to at least clean surfaces of the decks and heads. It may be that an original finish on the 6.0 block, that would be all that's needed. I haven't had that to try. Now, after finer sandpaper, and repeating the sequence 4 times. After about 6 hours of work, and this is why they invented milling machines, I'm in a comfortable range where I could use either the Felpro or Motorcraft gaskets based on the surface finish, using either the RA or the RZ standard. And I've also recorded the RT values. Using the top examples, I'm abrading down the surface. Usually RZ is a magnitude of 6 compared to RA, but the still existing deeper marks alter that ratio. I could still use those lowest milligrooves as a reference. And when I calculate the changes or correction of the values, RT can approximate how much I've removed from the deck. And it's less than 1/2 of a thousandth of an inch. So 6 hours of work doesn't get me into trouble. I've also rechecked piston protrusion, and it confirmed the numbers. How flat the deck is a concern, and the International Manual has different values for different spans. Ford just provides 1. Deviation to flatness is significant to sealing, but the deck is just one of the surfaces. And these values are given in consideration that the maximum variation of the deck may be opposite to what's achieved on the head side. We can't check how exactly they match up, so the values given to us by the manufacturer are based on that limitation. But if you can have one side flat as possible, you've improved the allowance for more variation on the other side, the head side. Using something like this doesn't give us that opportunity. I'm using 5/10,000ths of an inch feeler stock to show the result of this method. Across the 20-inch length, and then the 4-inch width. I was so distressed about the surface finish I didn't bother to check the prior existing flatness. But the most important aspect I'm trying to show is the technique from my experience only improves flatness, or at least it doesn't make it worse. The driver's side of the block was worse for poor machining. I started on this side to see if I had any chance of correcting the surface without tearing the block down and getting it all reworked at a machine shop. If I screwed up here, it was salvageable even if milling the decks then required shaving the pistons, so nothing to lose for me. But I also didn't think at this point I would be making a video of doing this. I just needed to document how bad it was. So you don't have to endure all the measurements, only the final. And some more music. And as with the passenger side, I was able to maintain the flatness of the deck. Both sides will see another pass of lapping with the 220 grit paper, just before the heads are installed. I want to ensure no oxidation of the surfaces, and there are a few areas that need some more work, based on the visual and profilometer inspections. I'm doing this for the first time with a diesel motor, and never went this aggressively to correct surfaces, mostly just to clean them for new gaskets, and dressing fresh machining marks. I'll have to see how well this does over time, but it's worked for me many times in the past. Once again, RZ values are higher than the standard ratio to RA, due to the deeper scratches that exist. But these are minimal to what the head gaskets were dealing with for 70,000 miles. I used foam to seal off areas to reduce the amount of cleaning after dry abrading the decks. Caulk saver foam for the holes and the coolant passages. For the larger holes, the pipe insulating foam was used. Any flat sheet foam could be used for the lifter areas. I patterned these with masking tape and then cut with a coping saw. Set screws just sealed the head bolt threads for extra protection. The 20mm size, the cheapest from McMaster. Plastic containers from the local supermarket were cut to seal the individual cylinders, and they worked very well. I later tried 4-inch foam discs from McMaster, which were about as effective, although I'd get the 1-inch foam next time.